So everything I'll speak about is a joint work with Joaquin, Cristobal, and Michele, who are all here. Okay, so what's the setting of my talk? So let gamma be a finitely generated group. And we're interested to understand the possible actions of gamma on the real line. So, which by this I mean just homomorphisms from gamma, the group of orientation preserving homomorphisms of the real line. And there is a standard reduction one can do. Of course, when you want to understand such actions, it's enough to restrict to actions which have no global fixed points. Because if there are fixed points, it's just a closed invariant set, and you look at the action on each connected component of the complement, which is still homomorphic to the real line. So, of course, we saw in Bertrand's course that a group admits such a faithful action if and only if it's left orderable. It's a very interesting question to understand which groups are left orderable and which groups are not left orderable. There are many examples and non-examples. But here I want to go a bit further, and assuming that there are such actions, I really want to understand their structures, so how do these representations look like. So let me give a name, bit ad hoc, to this set. Denoted like this chi of gamma r, it's going to be the set of actions on the real line without global fixed points. So to observation, first of all, this set is naturally a topological space. You can put on it, it's called compact open topology, which means that basically on omeo R you put just the compact open topology as you know it, and here on this set you put the topology induced by the product topology. So it's pointwise convergence topology on gamma with respect to the compact open topology on the target.
Sorry, is that other one?
Yeah. Thank you. And secondly, we are interested, of course, in understanding which actions are dynamically different from each other, so you can look at actions. Of course, it would be nice to look them up to conjugacy. Meaning topological conjugacy, but this is often too restrictive in this setting. The reason is that when you are given an action on the real line, you can always build from it many non-conjugate actions. Just if you're familiar with the Denjoy counterexample, if the action is only by homomorphism, you pick an orbit, for instance, and replace it by a sequence of intervals. You blow up this orbit, it's called, and you get another action which is not conjugate, but really looks very much the same. So it's convenient to consider another equivalence relation which sort of ignores and considers two actions the same if and only if they're either conjugate or obtained from two conjugate actions via this procedure. This is called semi-conjugacy. Let me give you the formal definition. So rho 1, rho 2 are semi-conjugate. If there exists an equivariant map from the line to itself, so where here gamma is acting via rho 1 and here gamma is acting via rho 2, we ask this map to be equivariant and non-decreasing. Okay. First time one sees this, it seems a little bit strange because one doesn't require the map H to be continuous. But this is just a compact way to say something like that. So let me explain a little what this means. It's a relation that works very well. So first of all, this is an equivalence relation. The reason is that basically you can invert almost invert an increasing map by looking like the supermoon of points which are less than your given point and the pre-image something. So it's symmetric. It's symmetric even if it's not completely obvious. And the second point is that so what does it dynamically actually say? So given a fact is that if gamma is finitely generated, this will always be the case in my talk, then for every action row of gamma is semi-conjugate to an action let me note it row bar, which is either minimal, meaning that all orbits are dense, or a slightly degenerate case that I like to call a cyclic action, which is very much not interesting, but you have to take it into account. So this means just an action that comes from an epimorphism of gamma onto Z, and then Z is acting on R by integer translations. Okay, of course, and moreover, rho bar is unique up to conjugacy, actual topological conjugacy. So in particular, if two minimal actions or cyclic actions are semi-conjugate in this sense, they are automatically conjugate. And in every semi-conjugacy class, there is an action like this. So if you prefer, yes?
Sorry, can you just say what cyclic is?
Yeah, you have an epimorphism of gamma onto Z, and then you let Z acting by integer translations on R. So to explain recall what it is, so fix mu symmetric finitely supported generating probability measure on G on gamma. Yes?
FS is
finitely supported. And recall the notion of harmonic action that Bertrand explained us. So we say that an action rho is mu harmonic if the Lebesgue measure is stationary, or an equivalent property is that the following. When you apply when you apply an element of gamma to a point in the real line, on average with respect to this measure, so if you do one step of the random walk and apply it to a point, this point doesn't change. So zero drift. But we saw
I have a question. Which your measure is generating?
The support is a generating set of G.
Okay, right. It's finally supporting generating measure.
Yeah. No, it's a generating set of.
Why generate? Why generate?
Generating means that the support is a finite generates gamma.
Ah, okay.
So what Bertrand shows us is that every action without fixed points on a finitely well, explain roughly the proof, finitely generated group is semi-conjugate to a harmonic action, which is unique up to conjugation by an affine map. Okay? So affine map means two things, means that it's unique up to conjugating it by translation or dilatating this. But however, you can also get rid of dilatation by just renormalizing the action. So let me say, let's call by h1 mu gamma R the space of all normalized mu harmonic actions. I don't want to recall what normalized means, but roughly speaking, so there was this Klepstein invariant that Bertrand introduced. It's a number that you can associate to an harmonic action that behaves well when you scale it. So you just ask that to be equal to 1. Roughly speaking, it just means that he showed that harmonic actions have bounded displacement, but this displacement could be very large. You ask that the displacement is close to 1. Okay? So this lives in here and is a compact space. It's a compact subspace of this huge Polish space, which contains a representative of every conjugacy class. And moreover, there is a flow on this space. Has a flow which is the translation flow, big phi. I will drop gamma r from now on. Which, what is it? Is just take an action and apply the flow at time t is conjugating the action by, this is tau t. This is the map that the translation by t. Okay, and so fact is that this compact space with a flow is actually does not depend on mu up to homeo and time reparametrization of the flow. So in particular, the partition into orbits does not depend on mu. Okay. Yes. So in here, you can look at subspace with this flow. And another fact, well, this is a theorem, essentially due to the run Klepstein Navas Parwani with some a little bit amended. So the point is that there exists a continuous retraction from the whole space of actions which preserving semi-conjugacy classes. And two actions in H1, I already said it, but I write it down, are semi-conjugate if and only if one is, they are in the same orbit under the flow. So okay. So what does this mean? In an action here, you project it here, and you have a representative semi-conjugacy class, which is unique up to this flow. And this sort of tells you why this space is bad, but it's actually not that bad. So the point is that if you try to figure out under this identification what happens here, this space, you can think of it as the space of orbits of this continuous flow. It's equal. And of course, it doesn't always make sense to do this. In general, this is a very bad space for a flow on a compact space. But it sort of tells you that this flow is exactly the abstraction for this space to be nice. If you keep it, you can try to understand it. And it also tells you that somehow the dynamics of this flow is exactly what you... So what you want to understand is sort of the space of orbits. And the more dynamically complicated this flow will be, the more it's difficult to tell actions apart from up to semi-conjugacy. While if the dynamics of this flow is very well ordered, the space of orbits will be nice, and you can hope to find them. So before I get to what kind of questions one can ask? So given gamma, your favorite group or your favorite class of groups, what kind of questions can you ask now about this space? So first of all, as I said, so how many semi-conjugacy classes there are, how rich is the space, and how bad is the Gaussian space? So how this will take a sense later with examples, I think. Is the Gaussian space. Second, a kind of question that I like a lot is which actions are rigid up to perturbations. So let me give a definition. Rho an action is rigid if its semi-conjugacy class is open. So this means that you take any action semi-conjugate to rho, you perturb it a little, it stays semi-conjugate to rho. So which actions, when does it happen? And so, of course, in the flow point of view, this corresponds to the fact this is just to find the open orbits. Another type of question you can ask, sort of 2 prime, instead of just looking at open orbits, is find interesting phi invariant open subsets. What is a phi invariant open subset? It corresponds to a family of actions which is robust, in the sense not just one action which is rigid in this sense, but maybe your group admits a very natural family of actions that you understand very well. You want to ask whether when you take one of those and you perturb it a little, if you stay in that family. Yes? I actually stuck. So sometimes it's called stable. Sometimes it's called locally rigid. Locally rigid would rather be it is an interior point in its semi-conjugacy class. So it just means under maybe stable. It's a better name. I'm not sure. Some papers call it rigid. Some papers call it stable. It means that if you take your action and you shake it a little, any action semi-conjugate to that, you won't change its semi-conjugacy class. That's the dynamical meaning. And a third type of question that is very interesting to study is mutability. So here, once you get a picture of the possible actions by homomorphism, you can ask which ones are actually conjugate or semi-conjugate to actions by diffeomorphisms. I won't write it down, it's clear. And also you can ask what is the regularity that you can realize. Okay? So let me start with an example. Very stupid example. Take the gamma equals Zn. Then what you can show is that every action rho of gamma on the line, of course without fixed point, is semi-conjugate to an action by translation. So this just means a homomorphism for gamma to the additive group of the reals. So, for instance, we can tell what is the space in this case, right? How do you prescribe an action by translation of Zn? You just say the image of the generators. They have to be not all 0, otherwise it's a trivial action. But then you have one parameter, you can renormalize the action by so this is the sphere Sn minus 1. And what is the flow? The flow is trivial. Because the flow is exactly take an action conjugate by translation, but actions by translations commute with translation. So this is an observation to keep in mind. What are the fixed points of this flow in general? They are exactly the actions of gamma that comes from homomorphism to the reals. These commute with translations and are exactly the only ones that commute with translation. And it's a theorem, very classical. It goes back to Plante in the 70s. The same holds if gamma is a finitely generated group of sub-exponential growth. So in particular, if gamma is virtually nilpotent. Actually, at the time when Plante proved this, it was not known if all groups of sub-exponential growth are virtually nilpotent. Okay, so this is a big class of groups for which the problem is sort of completely trivial. And sort of what is a natural next class of groups to look at? Well, what does somehow the smallest group of exponential growth? Well, one is very tempted to look at solvable groups. What about finitely generated solvable groups? And this is already much more complicated. So it's Plante, the guy who proved this thing that wondered about, motivated by that, about what happened in this case. So because, of course, the first guess you could do, maybe the same is true, but it's not true because there is one example. So main example is, well, you can look at the group of homomorphisms of affine transformations of the real line. Which is a metabelian group, and it has many finitely generated interesting subgroups. So there are many solvable groups that are on the line, not by translations, but by affine transformation. And so Plante speculated around the following question. So in a later paper around I think 1983, he asked, so under which conditions, if gamma is a finitely generated solvable group. When is an action gamma on the line semi-conjugate to an action by affine transformations. So to an affine action. So a first thing you can ask is whether this is true all the time. So basically, Plante wrote a paper where he was speculating, asked this question, and his answer was, there are many sufficient conditions, a bit technical in spirit, that imply that the answer is yes, but in full generality, the answer is no. There are examples of actions of solvable groups that do not do this. They are not affine. So let me So Plante showed that the answer is always yes. Always yes. If gamma has a finite Q rank, torsion-free rank, Hirsch length, whatever you want to call it, this is just for a solvable group, what you can look at is to look at its derived series. And so this is the derived series. The first one is the commutator subgroup, then the commutator of the commutator, and so on. It terminates because the group is solvable. And you can look at the rank of this thing as a torsion-free abelian group, which means basically you tensor it with Q. And you look at the dimension of this vector space over Q. And if this is finite. So this is finite for many solvable groups. For instance, polycyclic groups. Gamma satisfies this, or also among non-polycyclic groups, the solvable Baumsack-Solitar groups, which are famous subgroups of the group of affine homomorphisms of the real line. So in this case, the answer is always yes. Plante doesn't state it like this in this paper. He states this consequence. But the proof well read, at least these Cristobal words I'm reporting, where Plante well read gives you this. And but no in general. Counterexample. Is Z with Z, Rith product of two copies of Z. Let me explain why. So what is this group? I'll discuss for a moment. This is basically it's a semi-direct product of you take infinite direct sum of copies of Z indexed by Z, and you take a semi-direct product of Z itself that acts by shift in the space. And if you prefer, it's also given by an infinite presentation. There's two generators, H and T0. And the relations are that if you call Tn the conjugate of T0 by H to the power n for all integers, then you ask that all these commute. So let me try to do this discussion for this group. So what are natural actions of this group? So first of all, examples of actions. So first of all, this group, you can check that it has a non-trivial abelianization. Actually, both generators survive in abelianization. This is this square. So it has actions on the line by translations. Just send to generator two independent translations. Next, you have a family of non-abelian, so affine actions, which are actually affine, non-abelian affine actions. And how do you do that? You map H, you can map it just to any homotopy of the real line. And T0, you map it to any translation. Well, you can renormalize up to scalar factor. So the only case to consider is translations by plus or minus 1. And this actually defines an action of this group, and you check it by the presentation. Because when you conjugate a translation by a homotopy, it's still a translation, so it commutes. So for all lambdas, this gives you an action of this group. It's not always faithful. It's actually faithful exactly with lambda. It's a transcendental number. If it's an algebraic number, it's not faithful. But then, there is also a weird exceptional action I like to call Plante's action. How do you do this thing? So it's a bit tricky to construct, but so let's try to define an action as follows. First, row of H, we map it to a homotopy. What matter which one? Let's say by multiplication by 2, one generator. And the other guy, we try to map it to something which has fixed points, so it cannot be a translation. So define row T0 as something that on the interval, say minus 1, 1, that preserves the interval minus 1, 1, and acts with no fixed points in it. And for a technical reason that will be apparent later, let me also ask that it sends minus 1/2 to 1/2. And so what's happening here? This is the diagonal. So need a lot of colors. H is just multiplication by 2, so it looks like this. And T0 is something that acts without fixes these 2 points and acts without fixed points on it. So its graph will, you can suppose that it moves everything to the right. Its graph will look something like this. And now the game is, I only define T0 on a portion of the space, and the game is, can I extend its definition to the whole real line while preserving the relations? And the answer is yes, because what happens when I conjugate, so now the conjugation is just I started taking conjugate and want to check that they commute. But what happens when I conjugate this guy by H? So this is a homotopy, so if this is T0, its conjugate T1, so by a power of H, will be something that looks like this, where here is 2 and this is minus 2. Okay? And I want it to commute, but because of this condition, this guy will send minus 1 to 1, because I stretch it by a factor of 2. So this interval is a fundamental domain of this thing. Okay, so So when I ask it to conjugate, I have nothing to check where I already defined T0. And the fact that they commute tells me how I can propagate the definition of T0 up to here. And it will be something like this. Here you have a lot of little bellies that accumulate here. And this will be basically an orbit of this point under the yellow guy. Now I can continue. The smaller bumps? Yeah. So what are the endpoints, first of all? This is an interval which is a fundamental domain for this guy. So when I translate by the yellow guy this interval, I get this interval, then I get this interval, then I get this interval. And then I want that the yellow guy and the orange guy commute. I only define for now the orange guy on this part. I want to define here. How do I do it? I want that it's conjugate. So I conjugate back with the yellow guy here and copy its action here and continue. Okay? Now I can go on, and I can take bigger conjugates, and the picture becomes more and more complicated, but I do get an action of 0Z. And actually, there is only not one such action. So I can also observe that here I could have, this is a technicality, but it will be important right now. There are 4 such actions that you obtain through this, exactly 4 actions that you obtain through this procedure, which comes from the fact that if I replace H by its inverse or T0 by its inverse, this presentation doesn't change. So these are outer automorphism of the group, so I get actually 4 actions. So let me call this C, call this A, call this B. Now here is a proposition that we proved from every action of 0Z on the line is semi-conjugate to an action in A, B, or C. These 3 families are exhaustive. Okay? This is a bit tedious to prove, but it's a true fact. So now I can show you basically what's the space with a flow for 0Z looks like. So you see, wait, I need. I have 3 types of actions. Yes, yeah, this and the plantes. So as a topological space, it's just you take 2 disks and you join them by 2 points. It's the white shaded area. Okay. There are actions by translations which are the fixed point for the flow. Since it's a square, this is S1, by what I said before. And this is the red thing. Here is where the flow is trivial. Then you have actions by affine actions. And when you vary lambda, these describe the yellow part. So when lambda approaches 1, these actions tend to an action by translation. And then the flow moves slower and slower because here the points are fixed. And then it inverts. Okay? And in the future and in the past, you have to think this action, how does it look like? At infinity, only this guy matters. So actually, it's tending to an action by translation, which is a cyclic action, which depends only on this generator. So they all have the same limit points. And when you tend to the other thing, you have to converge to something. And from this picture, actually, you see that. So now that you know the compact space of this space of harmonic actions, so this construction of Plante is no longer so mysterious. So you found a bit like by hand. But you know that you have to converge to something. And there must be 4 different things you converge to. And the blue things are exactly those 4 exceptional actions you see there. Okay? no. So now let me tell you something. I want you to observe something on this picture. Is that the dynamics of this flow, what I said before, is very, very boring. Dynamically here, nothing is happening. Every point has a limit. It just chooses its limit and goes there. And as a consequence, the quotient space of this thing, so the space of orbits is very nice because you can draw a transversal to all orbits here. Take the red part and this white part I'm writing. This set intersects every orbit exactly once, and it's of course very nice, Borel, locally closed, whatever. And this is conceptually the reason why it's possible to write such a simple list of actions of this group, which otherwise wouldn't be possible. Okay? Running out of time, so I speed up a little bit, but then let me tell you now what I'm saying about the smoothability of these actions. So a proposition let gamma an action of, so always here Z, the group is 0 is Z. Consider an action by C1 diffeomorphisms on the compact interval without fixed point in the interior. Then the action on the interior is semi-conjugate to an affine action, to an abelian action by translation, or to an affine action. And how do you prove such a thing? Well, by this classification, the only thing you have to prove is that the Plante action, that specific action, cannot be semi-conjugate to a C1 action. And how do we do it? So let me just, for those who know, I won't write down because I am a bit running out of, well, no, yeah, maybe I can. Huh? How much?
11, 12 minutes.
Okay. So there is a previous work of Bonatti, Monteverde, Navas, and Rivas, very influential and very nice paper, which studied some actions by C1 of some specific examples of solvable groups, typically of finite rank. So in the case where you know already that topologically you have a semi-conjugacy to an affine action. But they show something which is called rigidity of derivatives for affine actions. So let me say in words what this means. Assume that you have an action on an interval by C1 transformations generated by two elements. So that by two transformations, which are, let's say, these two, a homotopy and a translation. So they generate an affine action. Assume that you have an action generated by two elements, and assume that abstractly it is conjugate, topologically conjugate, to an action by finite transformation generated by these two. Then what you can ask, something very common to ask in dynamics, is whether the topological conjugation must be automatically C1. This is not true. It can be topologically conjugate, but not C1. However, what they show is that even if the topological conjugacy is only continuous, it has to preserve the value of the derivative of this homotopy. At least for some lambdas, maybe for integers is definitely enough. Okay? So now once that you know this, and you have this picture in mind that the Plante action is actually a limit of affine actions, what would you expect? So this is basically the limit. What you up to conjugation is a limit of these actions where lambda tends to infinity. So if it was conjugate to C1 action, you would expect the derivative of that guy to explode. Contradiction. This is not quite a proof because the convergence is only topological, but what you can do is open up this proof, find the combinatorial structure that it uses about how intervals are moved around, and with this picture in mind, show that Planté action is not C1. And now, so let me say that from here, from the very good understanding of this example, you can show much more. So after combining with something I probably won't have time to talk about. Yeah. So I stated this as a proposition, but what is actually true is that if gamma is any finitely generated solvable group, then this thing is happening. And the proof involves understanding somehow the topological dynamics of arbitrary actions topological of solvable groups first. If I have time, I'll say a little bit later. And showing that if they're not conjugate to a affine action, actually technically you can find a subgroup isomorphic to 0 Z which acts in this way. So then from the proposition you get that here. And many other phenomena that you can see on this picture also hold true for arbitrary solvable groups. For example, always is gamma is a finitely generated solvable group. Basically, what is true is that the dynamic of the flow on the space of harmonic actions must be, again, very, very boring. So what is true? Take in the space of harmonic actions, look at the fixed points of the flow, which is always a sphere. What happens when you remove it? So first of all, so there is very nice, say, locally closed. I hope it's correct what I'm writing, but you can write something more precise. So locally closed section to phi orbits. So a section means just a set which is locally closed and intersect each orbit in exactly one point. So that's exactly what sort of allows you to say that the space of action is very, very nice and you have a hope to classify them, even though it's not at all true, but really not, that you have such a, like only 4 exceptional actions apart from affine actions in general. It will be very complicated, but this is still true. And 2, for every row which is not a fixed point of the flow, the limits exist, and there are opposite points in this sphere of actions by translations. So every orbit just in the infinity tends to an action by translation, and to minus infinity tends to the opposite action. So you can really say that actions up to conjugacy outside a compact set look very close to actions, a given well-defined action by translation. And the third thing I want to talk about is that for a vast class of four-bubble groups, say if gamma is a virtually solvable linear group of G ln K, then the set of actions that are semi-conjugate to a non-abelian affine action, to an affine action psi of gamma enough R, which does not take value in the group of translations, say. So, wait, no. The set is open. So, what does this mean? No, this is the nicest action solvable groups have up to the affine actions, and this says that this family of actions is robust in the sense that if you start from an action that you know is affine of a solvable groups and you shake it a little in the compact open topology, it must still be semi-conjugate to another affine action. In other words, you can deform it, but you can only deform it within this target group. You cannot leave this word. But there is an assumption here, and it's actually false for arbitrary solvable groups. It is not true. There are three-step solvable groups which are not like that and do not satisfy this. And I think I'll stop here. Sorry? Minus infinity. Okay, I'll stop here.